Hey everyone, I'm Nick, and welcome to version 2 of CUDA Crash Course. So in this episode of the series, we're going to be going over our first example of a CUDA program. We're going to start by going over some basic terminology, then we're going to look at our code, see how it executes, and then we're going to follow that up by looking at some of the low-level assembly that gets generated. That way we get a better feel for how our high-level CUDA code translates down to hardware. So let's go ahead and get started with the terminology with a brief overview. So the first thing is a kernel. So a kernel is just your GPU function. So we define a function that runs on the GPU, and we call it a kernel. And the reason why we call it a kernel is because it typically represents some core, highly parallel part of some computation. So in this case, we're going to look at, say, vector addition. That will be our CUDA kernel. Then we have our threads. Now our threads are just what executes the kernel. Then we have our warps. So warps are just how the hardware groups threads together. Now for NVIDIA GPUs, it groups them in groups of 32. Now this has a nice benefit. It goes back to the single instruction multiple thread execution model, where we have groups of 32 threads, but instead of fetching 32 instructions for those 32 threads, we just fetch one warp instruction. So hence the single instruction multiple thread programming model. So then we also have thread blocks and CTAs, or cooperative thread arrays. Now these are programmer-defined groups of threads. So the hardware groups threads, at the very low level into warps, but the programmer defines how many threads do I want in a particular chunk of the computation. So the programmer breaks up their computation into chunks called thread blocks or CTAs, and then all of those chunks together make up the grid, right? So your grid represents your entire problem that will be executed. So we define a grid for each kernel. So the kernel gets first decomposed into a grid. The grid gets decomposed into thread blocks. At the hardware level, that gets decomposed into warps, and all the warps are broken up into individual threads. So to give a better picture of how this looks, so we define the control flow for an individual thread. Our thread then in turn gets grouped into these warps, so we have to think about warps for performance considerations. Then all of these threads get defined inside of thread blocks. So these are just programmer-defined groups of threads, and then all of our thread blocks together make up a grid. Now it's important to note that our thread blocks are CTAs, and even our grid can be 1, 2, or 3 dimensional. And this is really just to facilitate when we have a problem that's, say, 1, 2, or 3 dimensional. It's a lot easier to map, say, a 2-dimensional problem to a 2-dimensional grid of threads. So the programming model has a flexibility to have multiple dimensions of threads, even though at the hardware level, it's really just executing, threads, and the, 2D or 3D aspects are just based upon indexes or indices. All right, so let's look at the hello world of GPUs, which is vector addition. So on a CPU side, it looks something like this. So we'd have something like a for loop. On iteration 0 of the for loop, we do, C0 is equal to A0 from B0. Then we go to the next iteration of the for loop and do C1 is equal to A1 plus B1, and so on and so forth. Now on GPUs, the reason why this is, the reason why this is highly parallel is because none of the iterations of, say, this loop are dependent on each other, right? They can all occur in parallel if we wanted it to. So in GPUs, all of these are basically tied to, say, individual threads. So we can break up this problem where every single thread will compute one iteration of that loop, right? And all of these can occur in parallel. So in this case, right, C0 is equal to A0 plus B0. This is occurring on one thread, while something like C3 is equal to A3 plus B3 is occurring on an entirely different thread. And all we really care about here is that at the end of the computation, we've got our final result array, say, our C array that contains all the results. So let's talk about indexing threads. So I said earlier that the way that we differentiate, the way that we define our parallelism is by defining a whole bunch of threads that will execute a kernel. But how do we tell them apart within the kernel? So we do that through some special variables that relate to the grid that we've defined. So let's look at an example where we have 1024 threads per thread block. And then we have 4 thread blocks in our grid, right? So these are the 2 programmer-defined parameters that we have for launching a kernel. So how many threads per thread block and how many thread blocks in the grid. So it looks something like this. So how do we differentiate between the 1024 times 4 threads that are within all of this entire grid? So we generally do it through something like a global TID or thread ID calculation. And it looks something like this, right? So it'll look like block ID x.x times block dim.x plus thread ID x.x. Now each of these are just built-in variables within CUDA. So your block ID x.x, it just indexes your individual thread blocks in the x dimension. And we're just going to be looking at a single dimension for this example. So just the x dimension, hence why they're all .x. Then we have our block dim.x, and this will just represent how many threads do we have per thread block. And then we have our thread ID x.x. So we said that we launched 1024 threads per thread block. So your thread ID x will be a valid index between 0 and 1023. Our block ID x.x has a valid index of 0 to 3, right? Because we have 4 different thread blocks. So what does this total computation do? So the first part, this block ID x times block dim, this gives us the global starting thread for each thread block. So for thread block 0, it'd be 0 times 1024. For thread block 3, it'd be 3 times 1024. Basically, we skip over the first 3 thread blocks, so 3 times 1024. Then the last part is basically the offset within a particular thread block. So this is a valid number between 0 and 1023, right? Because we have 1024 threads per thread block and it's 0 indexed. So for example, the first global thread ID is 0 because it's 0 times 1024 plus 0. Our last thread block, or our last thread in this grid, is 3 times 1024 plus 1023, which gives us 4095. Basically a 0 index between 0 and 4096 because we've launched 4096 threads, or rather 0 to 4095, right? Because we've launched 4096 total threads. And basically, once we do this calculation, we've differentiated all the threads in the grid. So every thread computes their own value. And now we have our way to indexing, say, into an array. So let's see a practical application of that inside of our code. So we'll start by opening up this vector add.cu. So the first thing we do is we have to set up our problem. So let's go to our main function. So we can define our problem size. So here we're just looking at arrays or vectors that are size of 2 to the 16. Or 65,536 elements, right? So that's quite a few elements. We could even push this higher to say be 2 to the 20, right? Or 2 to the 30 if you wanted 1 gigabyte of elements, or 2 to the 30 elements per array or per vector. So then we'll calculate ahead of time how many bytes this is going to take, and that's just going to be used later for allocation. So then on the host side, right, or the CPU side of things, we need to allocate memory. So it's important to know that GPUs have their own physical memory and CPUs have their own physical memory. So in this case, we're going to be allocating memory on the CPU side, and we're just going to use std vector for this. Right? So we'll have a vector of integers, A, that will have in different integers in it. Right? And then we'll have one for B and C as well. Now to generate some random numbers, we're just going to be using std generate from the standard library algorithms. So here we'll just go from begin of A to end of A, and we'll just use this lambda to return rand mod 100. Now this just makes sure that every single element of this A vector has some number between 0 and 99 inclusive. So this is just a quick way without using a hand-rolled for loop for just generating some okay random numbers, right? If you wanted good random numbers, you'd use something like from the random header, or use something like the Mersenne twister. So here we go ahead and get onto allocation on the GPU side. So far we've just initialized our data on the CPU side, but we still need to allocate memory on our GPU. And so to do that, we first create a couple of pointers. So DA, DB, DC. So we typically use D to represent that it's a device side pointer, or it points to device memory. A lot of times we'll use H to represent host pointers, or something that points to host memory or CPU memory. So then we call CUDA malloc, and this just allocates memory on the GPU side. So we pass in and DA, and this is because CUDA malloc takes a double pointer. So what this will end up doing is it just overrides DA with a pointer to GPU memory. And it's a pointer to, whatever amount we've calculated here in terms of bytes. So in this case, it's size of int times n. That's how much memory we've allocated at whatever DA points to. And the same thing with DB, same thing with DC, because we need a region for our A vector, our B vector, and then our C vector that's going to store results. We don't need to initialize our C vector because that's just going to be overwritten by the results of A plus B anyway. So we're not zero initializing that on the GPU. Then, how do we actually get our initial data over, right? So we created a bunch of random numbers. How do we copy them to the GPU? Well, we use CUDA memcopy. So here we're copying into DA from a.data. So again, a is just a vector, and we can use the method data in order to get a pointer to the data for that vector. So we're copying from a.data into DA. We're copying bytes, and then we're copying CUDA memcopy host to device. We specify the direction of the transfer. Then we do the same thing for DB. So we copy into DB from b.data. We copy bytes of data, and then we CUDA memcopy host to device. So, like I said earlier, the programmer can define a number of threads per thread block. Now in this case, the number of threads we're going to launch is 1 shifted over 10 times, and this is just 2 to the 10, or 1024 threads per thread block. So how many threads do we end up needing to calculate here? Or how many threads do we actually need to have every thread calculate one element of our vector addition? Well, we need in total elements divided by the number of threads per thread block, and that's how many thread blocks we need. So in this case, we'll have something like in div num threads. Now, what if in isn't evenly divisible by, say, num threads? Well, in this case, we need to do a little bit of padding here. So let's say we launch our in is equal to 1025. Well, 1025 divided by 1024, which is num threads, we're talking about integer division here, so that would give us 1, right? And now we have one element of vector addition that's not being calculated. So how do we make sure that we cover the entire problem? Well, you might see this in a lot of GPU code that you see, which is this quick padding, where you just do in plus num threads minus 1 divided by num threads. And this just makes sure that you always launch at least as many threads as you need. Now, in a situation like if you had in is equal to 1025, this formulation would give you 2 thread blocks, right? Which ends up being it ends up being 2048 threads, which is many more threads that you need, but it's at least 1025. So you'll have to handle those extra threads inside of your kernel, which we'll look at in just a second. Then we have our actual kernel launch right here. So we have our call to vector add, and our vector add uses these triple angle brackets right here, and this is where we put our launch parameters. So things like how do we launch our kernel? So the 2 ones that we'll look at today are basically our grid definition and then our thread block size. So basically what we do is we say how many thread blocks we want to launch and the number of threads we want to launch. And if we're just doing something like a one-dimensional thread block, these can be integers. So in this case, the first parameter is just the number of blocks. The second parameter is the number of threads, or argument rather. And then we have just, like any normal function call, we'll go ahead and just pass in some arguments. So then after our kernel completes, we'll copy back the data. Now it's important to note that your actual kernel launch itself is asynchronous. So when you launch a kernel to the GPU, when that function call returns, that doesn't mean the function is done, right? It basically just means that it's been launched. So we'll have to have some synchronization to make sure that the function is actually done when we want to read back the data. So in this case, CUDA memcopy ends up acting as both a synchronization point and as a way to copy back our data. So CUDA memcopy basically acts as a global synchronization barrier in this case because it's called from the default stream or the same stream that vector add was launched to. So if you don't specify a stream, it goes to the default stream and things within a single stream get synchronized. So CUDA memcopy won't start until vector add finishes. So we don't need to worry about any erases here. So then with this CUDA memcopy, we're just copying the data back to the CPU because when vector add finishes, the result is still just sitting on the GPU. We need to copy it back. So we'll copy it back into our C vector from DC, so that's our pointer to GPU memory. We'll copy bytes of data, and then the direction is CUDA memcopy device to host. So just the reverse as it was before. Then we'll run a quick function to verify the results, free memory, and then we'll just print out completed successfully. And if our verified results fails, our program will exit before we say completed successfully. So let's actually look at our GPU kernel now. So this is just the host side code that runs. What about the GPU side code? So if we go to the top of our program here, we've got our vector addition kernel. So all of our kernels start with this global, and this just says this is a function that gets called from the CPU but runs on the GPU. We call it vector add, so the rest of it just looks like a normal function definition. So kernels are void return type because they're asynchronous launches. They're not going to be returning anything. Then we just have our pointers that we're passing in. So our pointer to our A data, our B data, and our C result data. and then the number of elements inside of our vector, right? So then we go ahead and do our global thread ID calculation. So this is what we looked at in that presentation. So block ID x.x times block dim.x plus thread ID x.x. So at this point, every single thread has a unique thread ID, right? And that basically represents where it's going to index into the vector. Then we have this if TID is less than n. So this is the case where if we had, say, we launched more threads than we needed to. So such is the case where we've got, n is equal to 1025 and we're launching thread blocks that are size 1024. Now to cover all the elements, we need to launch 2 thread blocks, which means launching 2048 threads. Now only one thread in that second thread block is actually needed in that case. So the other 1023 threads, we need to make sure they're not just indexing out of bounds. So we do that by just doing a quick boundary check to make sure that whatever thread ID was calculated is less than n, because all 2048 threads in that example would be calculating a thread ID. So they're all executing this code. And this boundary check just makes sure that after we figure out that those are kind of, off the edge of our array, that they're not going to do anything harmful like indexing out of bounds. So then within the actual boundary check, we have vector addition. So all it does is it does C of TID is equal to A of TID plus B of TID. So no for loops in here because we basically flattened out our entire for loop into just individual threads. Every single thread or global thread will end up indexing into these arrays. They'll index a unique element, calculate one of the values or one of the results for vector addition. All right, so that's the basics of the GP program, and then we have our verify result. All it does is go over the size of the vectors, and then it goes ahead and just asserts if there's any value computed on the CPU does not match whatever was copied back from the GPU, right? So it's just a pretty simple verification to make sure that what we expect to have happen on the CPU side occurred on the GPU side. Okay, so we can go ahead and compile this, and we'll use nvcc to compile this. So this is our compiler from NVIDIA. We just pass in vector add.cu. Because we're using some C++11 things, we need to set the standard equal to C++11. And then on output name, we could just call it, say, vector add. Then after it's compiled, we have our executable here. And we can go ahead and run vector add like this. And we see that it completed successfully. So that means our functional test passed and our kernel ran. So if we go ahead and just do nvprof, so this is a profiler. It's since been deprecated, so we'll look at things like Insight CLI in later videos. But we can use nvprof to do a quick sanity check to see what's actually going on here. So this will go ahead and profile all the API calls that occurred during this execution. So we see that we've got 2 CUDA mem copies, H to D or host to device. So this is our copies into the GPU. Then we have 1 device to host, so this is the copy of our result out of the GPU. And then we have our kernel, so to calculate 2 to the 16 elements plus 2 to the 16 elements, it only took 7 microseconds, which is pretty quick. Then we have all the other API calls, things like CUDA malloc, device get attribute, CUDA mem copy, CUDA free, etc. So if we want to get a global timeline of events, right, we can use nvprof --print -gpu -trace. Now this will go ahead and give us a global timeline of these things. So we see that we had a mem copy, another mem copy, and then we had our actual kernel launch here, right? So this is our vector add kernel. It even gives us things like our grid dimensions and our thread block dimensions. And again, like I said, they're 3-dimensional, but here we're just using 1 dimension. The number of registers used, the kernel name, etc. And then our mem copy device to host. Okay, so that's the basics of GPU programming as far as this basic example. So let's look at how it translates into the assembly level. So we can use, just like there's object dump on the CPU, we can use CU object dump, and then we can specify the 2 different versions of the assembly that are embedded within our executable. So there's the virtual ISA called PTX, and then there's the machine ISA called SAS. Now the virtual ISA PTX, that gets JIT compiled or just-in-time compiled by the driver to execute on the GPU. And the nice thing about PTX is that you can have PTX generated for an older architecture, but the driver can just JIT compile it to whatever newer architecture you're trying to run it on. So here we'll just go ahead and we'll dump the PTX out of vector add. We'll just dump it to say ptx.asm, and then we'll also dump the machine ISA. So if we don't want the overhead of just-in-time compiling, right, we can also embed the machine ISA in the executable. So here we'll go ahead and dump out the SAS, which is the machine ISA. So this is what's actually executing on the GPU. So if we go ahead and open up ptx.asm, we see some assembly code here. So we can kind of make sense of this, and it's actually pretty easy to go through for something as simple as vector addition. So we see some parameters that at the very start of our kernel. So we see a load param u64. So these 64-bit things are just going to be our pointers, right? They're just addresses. So we have 3 pointers that get passed in, right? U64s, and then a U32 here. Now this is just a 32-bit thing. This is our integer in that we're passing in as well. So then you see some loads from special registers. So CTA ID, so this is our thread block ID. In TID, this is our block dim. And then our TID.x, this is our thread ID x.x. Then you see a multiply and add instruction. So this is our global thread ID calculation. Then we have a set predicate greater than or equal to. So we end up doing a comparison between R2 and then R1, our global thread ID and our int in. And then based upon that predicate that we set, P1, we either branch to the end of the program, which is down here, just to return. So this is if our thread ID is greater than n, so we launched more threads than we needed to. Otherwise, we go ahead and go down here and begin executing, the core part of vector addition. So we've got some stuff for address calculation here before we end up having these load globals. So this is all related to address calculation. And then we have load global. So this is just loading A and B, so into R6 and R7, and we just add them together, right? It's vector addition. So we go ahead and add R6 and R7 together, stored in R8, and then some more address calculation here, and then store global whatever R8 was, right? The result of, A plus B, right? And so that's how it looks from PTX levels, right? The virtual ISA. So it looks slightly different from the machine ISA level. So this is what actually gets executed on your GPU. And the different architecture, say SM30, SM40, this depends on the machine ISA for a particular architecture, right? So, modern architecture, say, I believe Turing are SM70, Volta SM60, Pascal, I believe, is SM50. So, and here we'll just be looking at, whatever default was generated for SM30, but we can also specify that from the command line within VCC as well, what we want to embed. We can embed multiple different versions of the SAS or PTX. So here we see something a bit different, right? So, we've got some similarities, right? So here we're moving into R1 some value, and then we've got some S2R instructions. These are just special to registers. So we're loading a special register here. And we see special register CTA ID and special register TID. So this is our block ID and our thread ID. Now your actual block dim is stored in constant memory, so that's what this move is. We have an integer multiply and adds for global thread ID calculation, set predicate greater than or equal to, so we're setting P0 based upon whether or not the TID is greater than n that we've loaded into, in this case, what we're loading in from constant memory here. So that's where n is stored, some parameter. Then we have, we're going to exit, which is just down here, if we want to, exit the program, if we're a thread ID that isn't a valid thread. Then we have the core part of actual, vector addition after this exit or this branch to exit, right? So we have some address calculations with these integer scaled add and moves, integer multiply and add, integer scaled add, but then we have our loads, right? So we have a load into R4, a load into R2, so these are just loading in A and B. Then we have finally just an integer add instruction of R2 and R4, so this is actually just doing A plus B. And then eventually we just store A plus B, which was stored in R0, into whatever address was calculated and put in R6, right? So there's some differences between the PTX and the SAS, but for something as simple as vector addition, we can see the translation between the two. All right, so that's going to go ahead and do it for this video. So that's the basics of GPU programming, how we define this parallelism and how we go from high-level CUDA all the way down to the low-level machine instructions or the virtual ISA that can be JIT compiled into the particular version of SAS for a particular architecture by the driver. So, as always, any of this code can be found at github.com/copybeforearch, so you can find it over here at CUDA Programming under Vector Edition, and then we have this vectorad.cu, so feel free to download this, play around with it. Let me know if you have any questions, and as always, I'm Nick, and I hope you have a nice day.